That must go there. Yeah, that does.
Gulliver's Laws.
That must go there. That does. That must go there.
Royal Institution Christmas Lectures. Lecture 5, Dwarf and Giant Numbers.
All right, thank you. Good luck. Up until now, we have been discussing, broadly speaking, the subject of size. Large things and small things. Large geometrically. Large compared to a meter stick. Or small compared to a meter stick. And sometimes heavy things. We've also discussed somewhat more difficult questions like energy and power and heat and all those physical phenomena. But we have not really talked about anything so far that was not measured against some units. We speak of power in horsepower, or we speak of resistance in ohms, we speak of size in meters, or perhaps in microns. But there are large and small things in our world which are not measured by comparing them with any man-made standard, but are counted for themselves. 1, 2, 3, like that. But certainly there are large numbers and small numbers. I have called them for this program dwarf and giant numbers. And numbers too, pure numbers, enter physics in a very important way. Always in the way that we use numbers as counts. We count something. We count atoms, we count events, we count for steps or collisions, and one after another we count them. We don't measure them against any arbitrary standard. We count them as individual objects of a big class. And it's most remarkable that in physics these numbers, large and small as they may be, play a very important role. What is quite striking is that Swift, or Gulliver as we have called, taking the point of view that it's a true account, Gulliver himself noticed really quite remarkable numerical things, which had nothing to do really with large people or small people, but had to do with large numbers and small numbers. And that is the topic of today. I'd like to read you about one of the things which Gulliver saw when he visited, and of course his purpose was not to describe science at all in a friendly way. His purpose is to make fun of the Royal Society of the day, in which he succeeded very well. But as I think most people have said, in the end, the scientists were to prove the match for Dean Swift. We may well criticize science today and be concerned about its effect on our lives, but not as Swift was concerned, because it was a waste of time, because it dealt with foolish and trivial and unimportant matters about which it had nothing much to say. That's not the problem of science, and Swift was simply wrong on that point. However, let us go ahead to hear what Gulliver saw when he visited the strange society of scientists in the city that lived beneath the floating island. It was called the Grand Academy of Lagado. And here is what he saw. The first professor I saw was in a very large room with 40 pupils about him. He observed me to look earnestly upon a frame which took up the greatest part of both the length and breadth of the room. He said, perhaps I might wonder to see him employed in such a project, but the world would soon be sensible of its usefulness. And he flattered himself that a more noble, exalted thought never sprang in any other man's head. Everyone knew how laborious the usual method is of attaining to arts and science. Whereas by his contrivance, the most ignorant person at a reasonable charge, with a little bodily labor, may write books in philosophy, poetry, politics, law, mathematics, and theology without the least assistance from genius or study. He then led me to the frame, about the sides whereof all his pupils stood in ranks. It was 20 foot square, placed in the middle of the room, The surface was composed of several bits of wood about the bigness of a die, but some larger than others. They're all linked together by slender wires. These bits of wood were covered in every square with paper pasted on them, and on these papers written all the words of their language without any order. The professor then desired me to observe the engine at work. The pupils took each of them hold of an iron handle, whereof there were 40 fixed round the edges of the frame, and giving them a sudden turn, the whole disposition of the words was entirely changed. Then they looked it over, they tried to find some good scraps, they recorded them, and he felt eventually they would be able to assemble all the books in all the subjects in the world by the chance assembling of random words. Here was what the artist of 1735, who illustrated Gulliver's Travels first well, thought the frame of Lagado would look like. This is a photograph of that old drawing. Here you see the frame, the cranks around the frame. Imagine a Lagado postgraduate student on every crank, and at a signal they all turn the cranks. These letters are in separate pieces of wood. They spin around, and whatever comes up they look over carefully. This is supposed to represent the words of the alphabet of Lagado, of the dictionary of Lagado, and then you read off these fine new phrases. Well, it's an absurdity, of course. Nobody would think of doing such a thing. But what I want to raise quite sharply is the question of why not? Why not? Why doesn't such a thing work? And it doesn't work solely because of the problem of number. It is number and number alone, arithmetical number, that prevents it from working. In fact, the principle is quite right. It would work, but it would work only with extraordinary patience. Patience and mechanical equipment far beyond anything the human world can ever contain. And as you will see, beyond even the contents of the universe. Let us try an example, a very modest example. I think we have some brave experimenters to do the Lagado experiment. Will you come forward, please? Thank you very much. They're going to operate the machine. We have a transistorized version of the machine of Lagado, still simpler and smaller. Actually, it's a very simple machine, as you will see. We did not build a great frame because we can calculate in advance how it will work, and we know it's not worth the effort. Show us what you have there, will you please? Tags with letters of the English alphabet. Which one did you get? Just read one. J, very good. And now we will shuffle these and draw one out. And as we draw, you will read off the letter, and Nicola will record the letter, and let's see how long we have to go before we get a recognizable word. 2-letter words are so simple we should get those rather soon. 3-letter words will take a while, and I'm not sure we can get any words of 4 letters in the time we're going to allot. So think to yourself how long it will take. Go ahead, let's run the machine.
T.
Very good.
G. H.
Nothing yet. I can't pronounce
B.
that.
E.
E. Well, there's a 2-letter word. You see that comes up quickly, but it's such a small word.
Y.
That's a 3-letter word, I think. Very good. Let's keep on going. That's quick for a 3-letter word, but it's an unusual one. Let's keep going to see if we get another one soon. You may have heard of the Bay of Tunis. He's that word.
T.
Not an easy task.
S. E.
Well, we're starting off again on a good one.
N.
N. Not too good. I'm disappointed. Maybe you'll get a 4-letter word this time. Let's hope for it. Next
R.
line. R.
E. P.
I think that's a 3-letter word, not a very usual one. Maybe there's some experts who will tell me about that.
T.
That was close to a good long one.
D.
Tad. I suppose we could count tad as a 3-letter word.
O.
Stretching a little. Ado. Ado is a very good 3-letter word. I think we've certainly got a couple of them. We'll try a little more.
M.
Now, with good luck, we might get a 4-letter word.
U.
I suppose that's a good Latin word, but if we start counting many languages, we'll be in trouble.
L.
Keep going a little bit longer.
X.
The famous domolks, a distinguished animal of the Arabian desert. Thank you very much. I think we've done the job very well. It was very good, a splendid machine. Hard work. Now, in fact, we went about 3, 6, 9, 15, about 30-odd letters. We did not get a 4-letter word. In fact, that's to be expected. You won't get one on the average for something like 100 or 150 letters. You get a couple of 3-letter words in that time, and we've done 1 or 2, a little bit lucky this time. Notice how slowly it goes, but it does work. So in principle, if we drew many, many things, we might expect to find a great many words and letters appearing. And eventually, since it's perfectly random, anything can appear by chance. We must be able to get any phrase, any book. So Swift was right. The Lagodans were right. Why don't we write books this way? Why?
Because it'll take too long.
It takes enormously too long. I have made a few sums just to give you an idea of how long it takes. And I will produce a sum which is so surprising that I myself found it difficult to believe. But I've checked it a few times, and while one could always be wrong, I think, in fact, it is really correct. If we tried to assemble words by letters at random and put them up into books, like this sturdy book. This is what I call a proper book of book size. Excellent book. It contains 2 million letters about. Now, in order to make the phrase which Gulliver used when he first visited Brobdingnag and saw the giant farmers in the cornfield, he said, "He appeared as tall as an ordinary spire steeple." That's all, not any longer than that. One small line like that. I have reckoned that to draw that line at random, even allowing for recognizing it with misspellings and a few letters turned around, allowing a generous recognition of the version of that phrase, if the whole earth, the land surface of the earth, were built solid with convenient libraries, holding books on their shelves like this, with space to walk around and look for books, book after book, full of these nonsense letters, imagine the expense of it all, and cover the whole earth with libraries as tall as the post office tower, you would then expect to find that phrase somewhere buried in those books. He appeared as tall as a spire steeple. Well, it's not a good way of writing books. People have much better methods, and the methods that people use are, of course, far deeper. In fact, random methods are difficult. It's difficult to make random things, and it's difficult to produce random letters because bias is the typical thing. You know, it's very hard to have a perfectly fair coin or a perfectly fair race. And in order to, people have managed to make books full of numbers which are, this is the strangest book of all. It would occur, of course, quite naturally in a book in my library covering the whole earth, but it even occurs in our libraries. It's quite a curious book because, well, this is a nice new book and I certainly don't wish to spoil it at all. I'm willing to do this, which is possibly a little unexpected. A perfectly nice little pamphlet. I have nothing against it. I don't wish to spoil it. But I just am going to cut the strings that hold it together. Ah, see, that one's already been mistreated. Here is the new copy. I'm just going to cut these strings and take the book apart. So, now there are not many books that you can take apart, but without doing them damage, but I assert that I do this book no damage if I rearrange the pages, shuffle them up any way at all. Now I claim, and I'm prepared to prove it, you can examine it afterwards if you want to make sure that I'm not telling a falsehood, this book is just as good as it was before I shuffled the pages. There are 2 ways in which that could happen. One of our experimental friends suggested one way. What is one way? Didn't you tell me the other day?
They're exactly the same.
If all the pages were exactly the same, of course it would make no difference. But not many people print books in which there are many pages all exactly the same. So if Mr. Tippett, who has written this excellent book, was not foolish. He did not repeat all the pages. In fact, they are not the same. Passively, we can see that. They're pretty small to see, but you'll see they're full of numbers. No two pages are the same at all. How can it be that their order does not matter? Yes?
There may be a set of tables all on one page. So
All
it doesn't matter any order.
No. The set of tables runs all the way through. In fact, if I take this page and throw it away, like that, the book is practically as good as it was before. It just has one page less. But the story is just as good. You miss nothing that way. It's just a little bit less of the book. Yes? They are random numbers. And therefore, random numbers, all that matters is how many you have. And which order they're in clearly makes no difference. That's what we mean by saying random numbers. And why do we have such random numbers put in the book? Of course, they were carefully made by drawing, some fair drawing. And they're printed here because it's much faster for us now to read off random numbers than it is to draw or spin. And we shall have occasion to use this later in the program. That is the way to construct a perfectly fair example of the Lilliputian machine, the Lagado machine. Now, if you want to ask how can probability then lead to other than this randomness, we remember something that happens even in our language, which happens in all parts of the real world, the physical world, and therefore I want to comment on it. It's related to randomness. If you want a complicated molecule to evolve, for example, the molecules of life, those complicated strands of nucleic acid and whatever was present in the earliest times, you cannot have those assembled quite at random. It will never happen. There are too many letters to go together to imagine that to happen. What you must have instead is a development of this kind. We humans assemble letters into words, words into lines, lines into sentences, sentences into paragraphs, paragraphs to chapters, and chapters to books, and books to curricula, libraries, subject matter, and so on. Because as soon as we couple things together, then when you draw them randomly, you draw some associated ones, and thus you can build up much more rapidly structures that have content and purpose than by the pure randomness. Therefore, it is most probable that the earliest evolution by chance of any important biological molecules happened not by all the atoms getting together at once and making the full thing, but by a slow step-by-step process in which first one small part came into being. Then by chance it assembled with the right other small part, and so on. And we see this done very well in biological systems today. In fact, this is a photograph, microscopic photograph on a high magnification of the apparatus which contains the information inside every living cell. This happens to be the human chromosomes, a three-dimensional structure that's squashed out in the microscope slide, highly magnified about 3,000 times, so that I don't quite see the number. But somewhere there, if I could see it, there is a number which indicates the size of the magnification. Well, I will simply tell you, yes, here we see it. Here we see this. One of those letters is about 1 micron in size. That's the smallest human beings can write, as perhaps we remember we were talking about the stereo scan. Each of these black stained objects, a human chromosome, is perhaps 10 times in dimension of the 1 micron, a little less, but it contains an enormous amount of information. So to speak, all the letters that spell out the word which is the human being's inheritance. And the point that I wish to make is that these are linked into little groups. Did you notice that? They were not one jumble, but little groups. These little groups represent the evolutionary history of the heritable characteristics of man. And it's quite characteristic that nature proceeds not by pure random methods, but very often by random methods which couple. Just as we make letters into words and then words into sentences, this kind of step-by-step development makes an enormous difference to the probability calculations. And if I put that into my calculation, it would very much shorten the time to choose books and so on. And this is how we can work. Now, that is not the only situation by any means in which produces randomness and the importance of randomness in the real world. Far from it. We have many other cases, and I want to demonstrate some of them, rather tricky cases, which are very often not included in a discussion of physics, except at the most advanced levels. And it's a pity, because they're not too hard to understand, and they're much clearer than the word reptatomux, which sounds very good, and I suspect will make a beautiful commercial product. But let us look a little bit at a very simple experiment, because I'm going to show you something you all understand very well, and then I'm going to attack the idea that it could happen. So, of course, you must believe what you see. You're quite right in that. If I'm not cheating, you believe that. It is true. But I'm going to try to show you that it's not as easy to understand as we would expect. Let me turn on a light. Here are a couple of identical lamps. Here is a exposure meter sort of device, a photometer that measures the strength, and a meter which reads what it is. It reads a little bit because of the room light, about a half. And if I turn on one lamp, I add about 2, so I get 1.5 for that lamp. Now let me turn on the other lamp. It's about the same, a little bit less. So a little bit less than 1.5 for that. Let us say the whole thing, instead of summing up to 3, would sum up to about 2.9, and the 1/2 to begin with should make about 3.4 if they add up. Let's see. They do add up pretty close, and this is what we expect. 2 similar lamps will give me, when I turn one of them on, 1 strength of light. When I turn 2 of them on, double the strength of light. If I turn 10 of them on, 10 times the strength of light. Everybody would agree that was the case. Can I have our skilled girls chorus, perhaps, for a performance, Monica and friends? The same thing that happens with light also happens with sound. These young ladies have practiced splendidly, and will give you a quantitative example of how this works. Monica, will you produce a nice tone for us?
La.
Now everybody. La. Very good, thank you. Now I think you can see, that will be enough. I think you can see that when one girl sings, she makes a tone, and when the other girls join her, they make a stronger tone. And if we were to measure it, we would find that 4 singers would be about 4 times as loud, 4 violins about 4 times as loud as 1 violin, and so on. There's very little doubt that that's what we must expect. Every experience teaches that. But remember that sound and light are in fact wave motions. And it is not perfectly obvious that wave motions will behave in just that way. Indeed, in the laboratory, it is extremely easy to produce wave motions. Perhaps not extremely easy, it is quite easy to produce wave motions that are different in that they do not add up that way at all. And that's a most important point which we must look at. Here we see what is a familiar ripple tank. It is a shallow tank of water, a pan full of water, with a bright light beneath it. You're looking at it through a mirror, and therefore you may be able to see the ripples in the surface in the mirror. If I put my finger in the water, I just make rough ripples, and it is water. Certainly works, just like water. And now we have this, we'll project the ripples on the screen so that they'll be more visible. And let us see what happens. I guess we need to darken now the room lights, and you'll watch the image on the surface of the screen. All right, Bill? What we see here is a peg just bouncing up and down, touching the water at the same point very rapidly, just as I did with my finger, only repeatedly, very rapidly, and making a beautiful set of circles of circular ripples spread out on the surface of the water. In fact, if you will move your hand in front of your face, looking through the fingers at the image, like that, but in front of your eyes, you will see more easily, perhaps, the pattern, because you make a kind of stroboscope. In fact, if you move it just right, you can see that you can make the pattern stand still. It's very attractive. And I think everyone can see that at all points here, there is a ripple passing through, and the strength of the ripple is about the same on any circular path. You would certainly expect that. Now, if I turn on another source, another dipper right up here, just the same, then if it is true that 2 girls singing make a louder sound by twice than 1, and 2 lights make a stronger light by twice than 1, then 2 dippers should make stronger ripples by twice than 1. Now I want you to look at the screen and see if you can think there's any place where that fails to happen. I just connect up the second, and now I think you see, in here, for example, or in there, slowly drifting, in that little channel, there's no ripple at all. Do you notice that? It's just flat and smooth. So that if I had been listening, if this were sound or light, and I'm listening there, turning on the second source would not have made it louder, but what? Made it quieter if it were sound, or darker if it were light, just as you say. Remarkable. 2 do not add up to make 2, but add up to make 0. Of course, the energy does not disappear in between, as you may well imagine. The second one does make it stronger, but there are places where it does not. In fact, if the 2 are not in tune, precisely, if I go off tune, then I can make it so that the channels, in fact, do not appear very permanently anywhere, and anywhere I look, I would in a short time have about, you see how the pattern just drifts right across my finger. There's no place at all where, if I moved in the right way, if I knew what to do, I could keep it quiet, but any place I would receive lots of ripples. That's exactly what happens in the real world. Whenever we have two lights or two sounds that are not precisely in step, then we add them randomly, and the random effect turns out to produce this simple result: n twice the light means twice the strength. Lights, thank you. Let us look at another case, which is another case of this curious algebra, curious adding and subtracting. No, I believe the fan has to be on. This is a pair of microwave sources. Notice they're precisely in step. You can tell that, very probably, from the symmetry of the experiment. The same klystron oscillator produces the microwaves going down these horns, and it splits neatly there. You see how similar these are geometrically? But it's pretty hard to imagine that they're any different when it comes out the end. And they're arranged to make this receiver work. Here's a receiving horn. The receiver makes a light when it's intense, and of course when it's not intense, I don't get much. If I close off the receiver, the light will go out. Let's try that. These pieces of aluminum are opaque to the radio waves, microwaves we call them, because they're very small wavelength. And now if I move, but I have two sources here. They're in step, like the two ripple sources. If I move this away, I can, by exploring, carefully find back here, it'll go up and down as the position changes. I think I have a position marked here where there's very little signal. You see, almost no signal. Both horns are present, almost no signal. Of course, if I close off the receiver, the signal is even less. But if I close off one of these sources, like telling one girl to stop singing, do you think the signal will get brighter or dimmer? Watch. Brighter. And if I close off the other one, not so good. This horn is not working. Ah, well, that's the way it goes. I would say there's nothing coming in this line. It looks to me as though, have we moved the line a bit? That was what was happening with the fan, perhaps. Can you give us more power? Oh, very good. There's much more from one horn, so that the matching is not all that good. That means, you see, there is much more coming. There's not quite as symmetrical as I thought, which means it's quite all right. I mean, the algebra will still work. It's just I have two that are working that are not quite equal, so I don't quite get to zero places in the same position that I had before. Let's see. I think this is still going to be all right. If I cover one up, I get a nice signal. Let me try to get a blanking, which I'm just not getting. There, I think I blanked the signal a little bit, and that certainly increases it. And that certainly increases it. So in both cases, the presence of the... If you turn off the plate, will be all right. So you see, the same thing can happen. You see, this is what we would expect if we are looking at wave motions. We would have to expect that that's the way they would work. That sometimes, when we have two lights or two sounds, they would not make it twice as loud, but would cancel. But in fact, that does not happen with two independent lamps or two independent sound sources. It only happens when we make them run in precise step, as you saw in there. And the random effect produces exactly the right result, as we shall see in a little while. In order to study this effect of randomness, the nicest experiment to do, the one which was done, first discussed mathematically here in the Royal Institution, more or less by Professor Rayleigh, who was professor here at the turn of the century. It was he who first put physicists straight as to how this thing works. He introduced the subject which he called the random walk. And let me describe a random walk. Birds sometimes are homing birds, like the close relative, the homing pigeon, which is relative to the beautiful dove, which we'll put on the screen in order to see how beautiful bird flight is again. But to remember that there we have this fine dove, and you've all heard of the close relative of the dove, the homing pigeon. The homing pigeon can in fact navigate so that when he is taken away from his loft after proper training, he can get back over 200 or 300 miles. And of course it's an important racing sport, especially well known in this country. But some birds can home in that way, and some cannot home reasonably. Some can only get home by random search. And the random walk that they actually perform is the kind of thing that we want to illustrate here mathematically, that is in a formal laboratory way. Well, let me tell you what the walk is. If I take a certain large shore bird from his home, he lives in the coast in Labrador, the gannet. It was done by a student of birds who followed the birds from a safe distance in a small aircraft, so he could watch the bird, and he knew exactly where it flew and how it flew. He plotted his own path. He had a hard time keeping enough gas in the plane to follow these excellent flyers. He took large birds, but he did the best he could. He took a bird in 50 or 100 miles, a shore bird that never went inland. He took it inland, and it started to fly, a very strong flyer. It flew a long distance. If it flew in the right direction, then in a couple of steps it would get to the shore. It knew the shore, it would find its way home. But if it didn't, if by chance it started off this way, it would fly for a long ways and become disappointed. Home is not that way, and it doesn't like to fly very far. Try something else. So it flew back in this direction. Then it flew back again in that direction, and then in that direction, and then in that direction, and in that one, and quite randomly. And finally, if it ever cut the coast, it was home again, quite soon. But this sort of path, which you fly and then by random choice decide to take a new direction, is called a random walk. And we will try to do a random walk by a couple of methods here to show you the remarkable results of randomness. And that will give an explanation for many things in physics. Let us try our random walking device. Do we have who's going to be able to start this going? I want to have somebody rather far back. Thank you. Will you start now? I'll tell you just exactly what we want you to do. We want everyone in this part of the theater to take part in the experiment. And the experiment consists in passing the ball either to your left or to your right or in front of you or behind you, always your nearest neighbor, one on either side, right? And which one you do will be determined by chance, perfectly fairly by chance. Have we a spinner to generate some numbers? Amanda, I think you will help us. Here is what we first tried to do. We have a spinner such as you might have at the, do you call it an amusement park here? Go ahead, spin us one. And let's see where it stops. What do you think?
Right.
Right. Pass the ball to your right. One. Thank you very much. You've done the first step. That's enough, Amanda. Thank you. We won't spin it anymore. Now, the spinner is a hard thing to make quite fair. In fact, we made one, and we tried the random walk a few times, and it didn't come out at all fairly. It was a biased random walk. Physical problems are very often biased. A little bit of tilt, a little bit of error in the bearings. This is a warning to you. It's a warning to you, as well as a statement about physics. But we have got Tippett's tables, perfectly fair, studied and tested many times, and therefore I will just read off some numbers and watch the ball execute a random walk around the audience. What we'd like to find out is, you'll remember who started it now. You're a very important point. Would you like to raise your hand, the starting point? Thank you very much. Keep an eye on the starting point, and watch how far the ball can move. I will now start reading left, right, right, forward, right, forward, forward, right. Off the edge. Very good. Very good. Now, notice how the ball moved in a random path. We didn't know where it was going. We might start with you again. No, we can't. You see, if we start, we're very likely to go off the edge, you notice? So we have to start again. We won't do that, but I simply want to show the nature of the random walk. Thank you very much. It was a beautiful walk to watch it make its way through there. And where it goes, nobody knows, cliche. Now, let me describe this a little mathematically, not to do any hard algebra, but just to write down some numbers. This is a series of lectures about numbers, and we mean them very seriously. There are three sorts of distances that we can talk about in this random walk. Of course, my random walk, unlike the bird, I wasn't free to go anywhere I liked. I was free to go only right, left, front, back. In other words, I made it on a square lattice instead of random. Much easier to do it that way, especially in a theater. So that's how we did it. So the path was something like this. I'll just draw this and stand out of the way. So you're allowed to go back and forth. It might forever oscillate back and forth. That would be very sad, but it could happen. And then it could do any such thing that it wanted. Now, one important distance is the distance from the start to the place where it left the edge of the theater. The start to stop, the end of the journey. And I would like to call that the airline distance. You understand what I mean by that? Not the distance the ball traveled, in fact, but the distance from the beginning of its journey directly in a straight line to the end of its journey. That's the airline distance. On the other hand, the distance the ball traveled is how much? It's a certain number of steps. Let us say n steps. In fact, I think I gave 11 steps. So it traveled 11 steps, each step being the distance between adjoining seats. That's the distance it traveled, let's say n steps. So this is the journey length, always measured in a certain number of unit steps. This is the journey length, but the airline distance is not the same as the journey length. When would the airline distance come out to be just the same as the length of the journey? When?
When you went in a straight line.
How could you do that? Yes?
It was brilliant.
Oh, yes, but I mean with this game, not in some other way. Yes?
You get the same thing several times running.
That's right. You'd have to get a long run randomly. Right. We almost did that at the end. Only 3 or 4. If we had a great big region, you see, you'd never expect it to go in a straight line. It will never go a shorter distance than that, right? It can't do better than putting all the steps in a straight line. But it can sometimes put them in a straight line. Can it also get nowhere in n steps? How could that happen? Yes?
Or if it went backward and forward.
That's right. It could go right, left, right, left, right, left, right, left, front, back, front, back, front, back, and many, many steps and no distance gained. What happens in the real world, then, cannot be predicted for any given case in advance, can it? We can do it over and over and over again and allow the average to come in, large numbers again. After large numbers of trials, we can get an expected value. And the remarkable result is, which we do not have time to work out, which you will certainly learn can be done algebraically and can also be done experimentally. What we find is that the spread of the journey, which could be anywhere from 0 up to n, the airline distance that we make for an n-step journey, but the usual value is about square root of n. So if we take 10 or 12 steps, we expect to make an airline distance of 3 or 4, which is not, we do a little better than that, but not very much. If we take 100 steps, what airline distance would you like to expect then? Yes? About 10. And 1,000,000 steps? 1,000, that's right. And so it goes. Notice how slow the airline distance grows with the number of steps. And that's quite typical. We see that in many, many real things in the world. I don't wish to say that they're all very simple to work out, but let us just try looking at a couple of them to give you the idea where you might see such things going on. And one of these random walks is often found in the case of liquids or gases moving slowly through media where they don't go always in the same direction as in a pipe, but where chance helps determine where they go. For example, if the dye stuff, which is a wood dye, is absorbed in paper, it makes its way through all the little interstices of the paper, which are woven fibers like that. And now it goes this way, now it goes that way in a kind of random walk. It's more complicated than the simple random walk. It's in 3 dimensions, and it's not absolutely random, it's biased because it doesn't go back into the wet place as often as it goes into the dry place. Moreover, it's alcohol, it's spirit, it's evaporating from the outside. So it's more complicated than the simple random walk, but it comes under the same class of phenomenon. And one of the signs of this is that it moves very rapidly at first and very slowly later on. Notice how that goes. Watch it go quite nicely. I didn't bend it very well. You can see it make its way up there, and when it's, you see if it goes like the square root of the number of steps, and the number of steps take each about the same time, then it'll go rapidly at first, and then slower and slower as our square root numbers go slowly. Remember, just as we tried it with the 100, 1,000. So if that's true, then if I start this one, which is just the same, at a very late stage, it will rapidly overcome the handicap. It maybe won't quite catch up, but it will be very much less far behind than you think, since the first part of the race is always much better, much faster than the second part. So you will see that the first one, he's not going to quite catch up, but notice in a rather short time, he's way more than halfway, and pretty soon that strip too will be at the edge of the dish. And I think that it's clear that if the speed were uniform or increasing, it would go the other way around. But here the race is only a little bit to the one who starts early. A similar effect can be produced with three-dimensional motion. Again, more complicated because the air in this room, while it's a fine three-dimensional volume, is not absolutely still. If I take a substance and try to send molecules from this substance to you, they will not go in straight lines, because the molecules of the substance will strike the molecules of the air. And when they strike, they'll bounce off, and or be deflected. They'll go in another direction. None will go in a straight line except by very good luck. They will bounce around in a random walk, and therefore they take a long time to get out there, even though they move at the speed of sound, very nearly, like a jet aircraft. Well, you can imagine how long it will take before you notice it. I hope that when you smell something interesting, I won't say it's very beautiful, but it's not bad. When you smell something interesting, raise your hand, and what we'll try to see is if we can notice any progression of hands as we go back into the audience. I will now spill out this excellent spirit-containing material and see what happens. The nearest people, and then those behind them, and then some back there. And now it is really spreading through the audience. And I think you get the idea. There is a general random walk of the molecules of scent out to our detectors. Thank you very much, detectors. You're excellent indeed. Let us then try another experiment. And here too I have some assistant experimenters who will do the job for me. Here we have fascinating. You want to start the clock? Very good. Here we have a very interesting system, a familiar Geiger counter excuse me a moment, this silver cylinder here contains a sensitive chamber of gas which detects the presence of radioactive material. And here we have a very weak and quite safe source of radioactive radiations, a little bit of radium in a bottle. The bottle protects me from putting my fingers directly against it, which might be a little bit unhealthy, but if I stay away at that distance, there's no great problem. And we place this in the proper position so we get a reasonable counting rate. And you will hear a click when the device is working. You will hear a click, which is the amplified detection of a single ray coming from this source and penetrating the Geiger counter. Perhaps you can see the pulses on the meter already, which indicate silently exactly the same phenomenon. Now what we're going to do is to make a sample. This is quite a random effect. No one can tell you. It is pure chance which determines which atom of radium decays and when it next decays. So we're going to make a succession of measurements to show this spread and try to indicate the most important thing of all, which is that when we get to large numbers, the relative spread will drop farther and farther. Let us then try. Michael will give us 5-second intervals. Everybody can count the clicks quietly, and then at the end will be a recording. 1, 4, 3. Put up 3. Very good. Does anybody else hear that? Let's be quiet and try another one. Three. Very good. Let's try another one. 1. Very small. Is that what you got? Try another one. 4. Possibly 5. What do you think? 5? Very good. Well, you know, now one more we'll try on this batch. Did you get any? No. 0. Oh, you didn't switch it on. Oh, it has to be switched on. All right. We'll try it again. 2. All right, try another batch. Make a line and draw another. Good, thank you. Let's try another group. Five. Very good. Six, perhaps. Yes. Many at once. You notice how strange this randomness is? Sometimes you wait a long time and none, and then suddenly 2 like that. That's random. None? Wow. And again? Seven. Six? Six. All right. We may miss by 1. We can't tell. Four. Is that right? Very good. Thank you. That's a very good experiment indeed. Let's give these experimenters a hand, I think. Now, notice what we were saying. Notice the spread. These are the same. We measured each the same time. They should each have about the same number. But in each interval, the intervals go from 1 to 5 in the same interval. And here from 0 to 6. What is the average number here? Well, we can see this is 6 plus 7, 13, 14 over 5. That's a little less than 3. I'll say 3 minus. And here we have 10, 21 over 5. That's 4 plus. So you see, the bigger samples, as we call them, are pretty close together. That isn't a very big error, though we had only a very few counts. We expect an error which is about the square root of the number of counts we have. So if we have about 20 counts, the error should be about 4. And that's about 1 part in 5. So that's about what we're getting, an error of 1 in 4 or 5. Whereas an individual one, we have only 3 or 4 here on the average. So we expect an error of the square root of 3 or 4, which is like plus or minus 2. And so you get everywhere from 1 to 6, which is the sort of thing we've just said. So you see how it works. And if we counted thousands, we would come out with very different numbers. But we would always expect to have the relative number practically the same, which I think is an extremely interesting result. In fact, quite generally, that's what we get, that the spread of a random sample of n steps, like the random walk, is just proportional to the square root of the number of items in the count. That is the great law which Lord Rayleigh applied first to sound and light. Let's go back to the sound and light and describe why they are as they are, and I think we can do it in the following way. The strength of either sound or light, I'm using simple words. I could, of course, say intensity, but I think you'll understand strength to mean much the same thing, less technically. Sound or light is proportional, and this is the interesting part, to the square of the disturbance that produces it. This is true for the ripple, too. To the square. Anyone who has studied the physics of waves will recognize that the energy is proportional to the square of the amplitude. That's more technical language. I will say the strength is proportional to the square of the disturbance. Therefore, if the disturbance adds up, as it would if I have several lamps or several sounds or several microwave, and they all add up in the ordinary way, we'd say the disturbance would be proportional to the number of sources which we had. And then the strength would be proportional to the square, by this rule, to the square of the number. And thus, 2 singers would be 4 times as loud as 1 singer, 2 lights 4 times as bright as 1 light, a ripple from a double source 4 times as great as a ripple from a single source. Can that happen? Yes, we've seen that it can happen if they're exactly in step. But it could also go, if they're exactly out of step, all the way down to 0, as we saw here. 2 together give 0 because you add 1 to the other with the opposite sign. The total disturbance goes to 0, and therefore the strength can vary from n squared down to 0. But in the real world, not in the physics laboratory, it's part of the real, I shouldn't say it's not real, but in the uncared for world, the world of things that happen for other reasons, 2 singers are always twice as loud as 1. 2 violins twice as loud as 1. 2 lights twice as intense as 1. Because they're not made to be in step. And how can it be that the strength is twice as great? What must the disturbance be then if the strength is to be twice as great? Can you see that? The disturbance must be the square root of 2 times as great. And you see that's exactly the rule we had for random walk, the square root of the number. So if the random disturbance, if I say a random disturbance goes like the square root of the number of disturbers, random disturbance proportional to the square root of n, then the strength will be proportional to the square root of n squared, or proportional to n itself, and the strength of a pair of lights is double the strength of one light, and so on. And that was the famous proposition of Lord Rayleigh, which is there. And I find it quite remarkable to think that the random walk, like the soccer ball through the audience, is present whenever we hear a conversation or an orchestra or turn on the lights in a room. It's very interesting, and of course physicists is very anxious to study the cases when it doesn't happen as well, but it does happen in so many circumstances. So that is very reasonable, and we feel no concern about it. And I think you've seen how these matters work. Let us look at a set of numbers. Somebody did a nice experiment, which I will not repeat. It's a little tedious. Perhaps you know what these objects are? Playing cards. I'm not going to play a game, but I'm going to report the result of a mathematician who played the game with a fair shuffle and drew 25,000 nearly cards from the deck, again and again and again, reshuffling all, just as we drew tabs from the box. But 25,000 is a long work. I think he worked in spare time for 6 months. Now, what did he find? This is the interesting result. If you have followed my argument, and if you're quick to jump to conclusions, you will be able to give the results that I'm going to write down. But I want to write them down so that we have the numbers of an actual experiment to compare with. And I think it works quite well. Let us look at these numbers and see what they are. He drew 24,965 times, which is a good large number. And a fair deck, of course, he removed the joker, just as we did. I think that's a joker there. Will you pick it up and expose it? Yes, very good. We removed the joker, and therefore the deck equally contains hearts, diamonds, clubs, and spades. How many of these would you expect if everything's perfectly fair? You would expect that you'd take 1/4 of the 24,965, which is 6,241 and a quarter, if you like to do your arithmetic closely. So if I did this many, many, many times, and a fair deck is present, then I will expect to see just that number of cards coming up if there were no randomness around the distribution. This is what we get in the case of large numbers. But in fact, what he got was 6304 hearts, 6236 diamonds, 6131 clubs, and 6294 spades. Now compare what he got to the expected average, 6241. Nowhere does it differ by more than 100, and it's usually about 50 off. Now the square root of this 6,200 is about 80, a little less, 79, say 80. So we'd expect that most of the time he'd be within the square root of n, within 80 of this number. And you see, most of the time it was. The smear is about the square root of the number of times you have the sample. And that's a very general result, which is just as true for lights or atoms as it is for playing cards whenever there's an unbiased draw, and is the heart of the statistics of large numbers which enters into physics. Whenever things come out with precision, without errors, then you know a large number of atoms or a large number of some fundamental thing must have been involved. And this is the basis of our belief in the accuracy of quantities in physics. It is always a problem of giant numbers. Now, to show this a little bit more graphically in other cases than simply numerics, it is worthwhile looking at what we call the Brownian motion. I hope you've heard of this. Robert Brown was a botanist in London, here in London, who lived about 140 years ago, 50. And he found that if he put small grains of pollen and looked at them with his microscope, put them in a suspension in water, and looked at them with his microscope, he often saw them, as often as he looked carefully, dancing forever. Even if they were dead, they appeared to dance. He thought at first it was because they were living. And then people learned that you could do it with powdered sand, anything, whatever. Dances incessantly if it is small enough and look at it under the microscope. I think if you will watch Bill put the microscope on a sample which contains a fine suspension of red powdered pigment in the suspension of water, and the microscope can magnify it up, and when it is adjusted, about magnification about 600 or 800 times, you will see, lights down I think please, you will see on the screen the in focus moving particles. You notice how they dance forever. It's worth watching. It's a beautiful sight. And this has nothing whatever to do with their life or their nature. Any particles sufficiently small, placed in a fluid or in a gas where they're free to move, will show this motion if only the system is at the temperature of the room. You can't get rid of this motion no matter what you do. We'll talk about that in the last lecture quite a lot. Notice how it goes in a random way. Now, to give some feeling of what's going on, we have a model here. In the model, which you will see projected on the screen, we have a set of mock molecules. No, I think we want lights down, please. No? Mock molecules, which are simply small steel ball bearings, 1/64 of an inch across, like the Feynman motor, magnified up here, and caused to move by a magnetic field which is whirling around, causing them to move in a somewhat random way. Notice they're not precisely random. They tend to stick together, just as you'd expect. And they fly in all directions at that impurity, like a big piece of pink pigment, which we'll show you presently, just a piece of paper. And it is sometimes hit on one side, sometimes on the other. And since the number of molecules that hit it is random, why, of course, sometimes there's an unusual number on the left and not so many on the right, in which case it moves to the right. And so it goes. It does then a random dance. And that's exactly what is happening in the real Brownian motion, which we can look at again. In the real Brownian motion, you cannot see the molecules. All you can see are the large impurities moving about as the molecules irregularly press them in one direction or another, because the molecules, of course, are in constant motion, and the Brownian motion is the reflection of molecular motion by things that are large enough to be seen in the microscope. Even a brick would show Brownian motion, but the motion is so small that we can't detect it. Only in small particles does the scaling allow its detection. I think that's enough now. We can have the lights, and Bill will show us the small piece of paper which was the Brownian motion impurity in the model. Of course, the real one is enormously smaller, only of microscopic size, because real molecules are not little ball bearings, you understand quite well. Now, Brownian motion is to be found not only in the case of particles where it is first recognized and where is so beautiful to see in the microscope, but it also occurs in all kinds of physical apparatus wherever random motion can be present. And that means almost wherever electrons or atoms or molecules can be detected in large or small numbers. If the numbers are not too large, then the fluctuation, as we call it, the deviation, the difference from the expected number, the square root of n, is real. And so these square root of n differences always show up. And if we have any amplifier, then the voltages in the amplifier, that which the amplifier detects, the little currents, are never zero. They always have some little effects, because though on the average the electrons want to stand still, they still have random effects which make them move one way or another. And this, for example, we can hear in an amplifier which is turned on with no signal coming in, but with powerful gain. I think we might hear that sound. Without pattern, formless, but it's perpetually present. It is the very noise, in this case, of a radio circuit open to the arbitrary disturbances that come in from all of London and to the heating of the electrons on the filaments of the early valves and so on in the amplifier. We always get a fundamental noise. And of course, we look at it in a video amplifier, a television style amplifier. We see the noise. Strange to think of seeing a noise, but that's the language we use. We see the noise as a patternless series of spots being amplified up again the same sort of input, just a formless number of voltages because of the random motions and random causes. I think you will see that on the screen. And there, this thing which is often called snow because of its similarity, fancied similarity to snow, is another sign of the presence of perpetual motion, if you like, in the random events that occur on the microscopic scale. Now, this sense that behind the level of physics that we normally talk about, the voltages we read in our meters, the sounds we detect in our amplifiers, the sense that that is present is always true. But it is never really quite true. No measurement is ever really precise. No measurement is ever free from the errors as long as atoms and molecules and electrons and chance disturbances are present, which smear out every result and give it this trembling effect. If it's large enough, if large numbers are present, then the trembling effect becomes arbitrarily small as you like, just as we saw with the drawing of cards. Imagine if we drew millions of cards, calculate for yourself how little the differences would be. But those differences are always present, and the sign of the distinction between the modern physics, where we deal with atoms, electrons, and particles, and the classical physics on which we build, which deals with measurements that are precise. The difference is the difference of whether we deal with dwarf or giant numbers. Thank you.